are wrong. I shouldn't say they're wrong. The numbers aren't wrong. The way they collect the data is wrong. I talked about this a little bit in the last few weeks, didn't I? Did I talk to you guys about it a little bit? How do they collect data for polls leading up to an election? They call you. If I need to find out, okay, how are people voting in New Jersey? I need to poll 1,000 random people in New Jersey randomly. So I have to call them. I'm not going to go to their houses, and it's much more efficient to call them. So I call. But the thing is, when you get a phone call from a number that you don't recognize, you don't answer it. So if I want to get 1,000 people in my poll, which is pretty much the industry standard, I'm going to have to make 200,000 phone calls just to get the right number of people. That's really messed up. It's not possible. The polls are wrong in that sense. They're not being collected properly, which is why all of these jumps happened. Now, my predictions were actually pretty close. Check this out. Hold on. Oh, yeah, for fun. This was my, you see what I highlighted there? That was my adjusted prediction. My adjusted prediction based on how I felt the polls were going to go based on various variables that I had. And this is actually pretty darn close to what it's actually going to end up being. I felt pretty good about that. In fact, I was pretty close on a lot of these things. Like I said, you could see it right there. My success rate. We'll see what happens. There's still a bunch of races up for grabs. Here are the remaining votes everywhere. For the states, the Senate, and the House, there's 2 more races in the Senate, but they're not going to decide those till January. Look at this race in Iowa. The difference between the vote totals in Iowa. That's pretty funny. 48 people is just a couple of class periods. Anyway, can't wait for 2022. You know what's happening in 2022? What'd you say? You vote all over on this again. There's a third more Senate seats up for grabs, and all the houses up for grabs again in 2 years. Did you know that? Every 2 years they vote on the House of Representatives, the entire thing. Anywho, back to this. What in the heck? Mr. Mark's room. Hey. Oh, goodness. I thought I had done that correctly. Give me 1 second. I just got to look at it. Oh, goodness. I could have sworn I saw somebody there. See, now I'm doubting myself. I could have sworn. Hold on. 1, 2, 3, 4. I had 7 people in the homeroom. And I only had 1 absent, and that was Priscilla. Is it? Okay. I apologize for, yeah, I really, I could have sworn I saw her this morning. I know she hasn't shown up a lot. Okay. All right, bye. Stupid attendance issues. Anywho, here's what we're going to do. We are about to take a step towards the next unit. You all know what's happening next week, right? You don't know what's happening next week? 5 days a week. Yeah. And then eventually we'll be shutting down. Yeah. You all see these things over here? Hold on.
Yeah, I saw a bunch of those just now.
This is what next week is going to look like.
Yeah, it's not.
But what's the point of getting that?
This is what.
The point is, well, I'm sorry, it's going to have to stay up though. The reason why it's going to have to stay up is because the administration is going to be making sure that we have all these up. The reason why they have to go up is because of the new guidelines, which state that if you have more than 15 minutes of continuous interaction with somebody within 6 feet, then you are possibly exposed.
I think this is going to change it.
No, it won't change a thing.
Change it.
It won't change a thing. I know. You can see me smiling, hopefully.
Yeah.
Yeah.
This is the dumbest thing ever.
It is. It so is. But I still have to do it.
Do they make them move themselves?
I don't know. I got a bunch of them over there.
Oh, no.
I don't know. We'll see what happens.
So stupid.
They really are.
This is literally, it's like first grade again.
Yeah.
Those are like anti-cheating things.
Yep.
You know, it's when you put your own folders.
Yes, I remember that. That was great. No, but what's going to end up happening is people are either just going to be like, or just, I'm going to look around the side. It's not going to do anything. It's not going to do a blessed thing. I've been sending pictures of this to like other colleagues of mine who are not in the school, people that I know that are teachers. It's just super funny. They're just laughing.
They're not doing the same thing.
Different schools are doing different things. Some schools are not going 5 days a week. Like Lacey is sticking to their hybrid schedule.
It's more like
Honestly, I don't know why we just don't stick to that.
yeah, it's
It's
just
kind of working.
It is and it isn't. It is and it isn't. There's pros, there's definitely cons, but
Why are you going back 5 days a week after experience?
yep,
I feel like there'll be more cases.
yep. Have you seen the COVID list? Hold on, let's go to New Jersey. Check this out. I actually booked time for this. Look at this. Next week, though, everybody's got one.
yeah, BS.
I know, but next week everyone's gonna have one. So
You're not no room like that.
I know.
What am I gonna do? Like buy like a computer and then my papers.
I'm gonna be very clear. I'm gonna say this in the microphone so that people can hear me as well. It's ridiculous, but crap rolls downhill. It does. So if the crap rolls onto me, the crap has to roll onto you. So if they say, Mr. Markey, it's procedure. You need everyone to have that thing on their desk. All right, because you know what they're going to do? They're going to walk around the school. They're going to look in the doors. And be like, Mr. Markey, you don't have all your students with those things on your desk? No, I'll get in trouble.
Are they gonna fire you?
No, but I will get in trouble by not following my procedures. Dude, tenure doesn't exist. Tenure is a fake thing that students think exists. You think teachers can never get fired? You kidding me? I know a lot of teachers have gotten fired. Now, here are the numbers right here. You see where I'm pointing? That was March 16th. That was when we went into lockdown. This is after March 16th. This is when schools came back. Here's where we are now.
So why aren't we just like not like I'm fine with being home?
It's not my call.
Honestly, if we don't have to do like the video calls and stuff, then it's not. Video calls is such a waste.
You guys know the schedule for next week, right? No, it's an 8 week. Hold on.
Wait, they're doing weeks of like 8 days.
Yes.
Are you serious?
Yes. Where's the email? I had it here before. Did I get rid of it?
So, like,
Is it in my drive? Next week is an A week. There it is. I found it. Starting Monday the 16th, we got an A week. It's going to be 10 minutes of homeroom. You're done at 7:20. Then you have an hour class and then a 4-minute passing time. An hour class and a 4-minute passing time. An hour class. And then, well, there's 8 extra minutes in fourth period. And then you go home at 11:40. And then there's this block of teacher lunch right here. And then in the afternoon, you see all the stuff in gray? That's not you. That's on me. I have to do all that stuff in gray. But then on Tuesdays and Fridays, that's when we have our virtual Google Meets. Fun fact, they're all 10 minutes long.
Wait, what?
They act as office hours where you can check in, but it's not required. Starting next week.
Wait, what time is like the virtual?
Tuesdays and Thursdays, or Tuesdays and Fridays.
You don't have to join them.
Yeah.
Well, like, wait, if you're gonna be back 5 days a week, what time is it on Tuesday?
Starts 12:30.
What time? Wait, they want us to join after.
No. That's for virtual only.
Oh. This is too much work.
Yeah, probably like a few more. We'll see. You guys ever Ever heard of designing a camel? The theory behind designing a camel? It's you get like a bunch of people together, like a group of people, and as a committee, they have to design a horse. And so they all take different aspects of the horse, trying to design, okay, I'm going to design the legs, and you'll design the head, and you'll design, the back end, whatever. And then when you put it all together, it looks like a camel. It's the idea that like when you have too many people working on something that seemingly should be simple, I'll close it. When you have too many people working on something that should be simple, it ends up being a monstrosity. That's what this is. I can't help you there. I'm not really familiar with it. Ladies and gentlemen, look at the board. Look at the board, look at the board, look at the board. Look what I got there. I got a linear equation. Y equals 2x plus 1. This is a polynomial. Now, I'm going to give you the definition of what a polynomial is in a moment, but this is a polynomial. It is what we call a first-degree polynomial. This is a second-degree polynomial. Now, hold on. There's a hurricane happening. There we go. Actually? No. I think he believes everything I'm saying. Now, this is a second-degree polynomial. This is a quadratic. We've been dealing with these for 2 months. But it's a second-degree polynomial. The reason why we call it a second-degree polynomial is because of the largest exponent that is on the equation. A linear equation, the line that we saw before, that was a first-degree polynomial. The largest exponent was a 1. But now, we are getting into some heavy-duty stuff. What's going to end up happening over the course of the next several class periods is we're going to be getting into stuff like this. This is an example of a third-degree polynomial. Just one example. Obviously not a straight line. Obviously not a perfect parabola. It's kind of this little wonky, wavy thing going on here. But it's a third-degree polynomial. A third-degree polynomial is called a cubic. They all have names really up through the fifth-degree polynomials. Beyond that, we just refer to them as like sixth degree, seventh degree, stuff like that. It goes linear, quadratic, cubic, quartic, quintic. I know. But these are different levels of polynomials that you could potentially have. Now, these things don't act like what you're used to. They do all sorts of wacky, wavy moves. For example, I could put up a fourth-degree polynomial here. Put in an x to the fourth power. Let's do plus. Let's do minus that. Oh, there we go. Minus. Oh, there we go. Hold on. 3 there. And then we'll do plus. What happens there? No, I don't want to do that. Minus. Nope. Go back plus 1.5. There we go. And then we'll do a minus 3. Plus 3. There we go. Look at that thing. Looks like a tooth. Like a dagger. This is an example of a fourth-degree polynomial. You're about to get into the realm of polynomials that you never thought you would ever see. But the thing is, life is not always going to be a straight line. Life is not always going to be a perfect parabolic arc. In reality, when it comes to modeling real-life behavior of various things in life, you're going to need higher-degree polynomials in order to get a more accurate view as to how things actually move. It's really nice. So what I'm going to need from you, ladies and gentlemen, I'm going to need those notebooks out and open. Where did you go? There we go. Now, this is going to be a little bit of a crash course into the idea of polynomials, but this crash course is going to inform the entire next unit of information that we are going to be covering. I suggest that you write down all of these definitions and examples that I have, because I'm about to take you on a journey. This is Intro to Polynomials. Today is the 12th. Yes.
I don't got it.
If you see where all of those stupid dividers are,
Yeah.
the ones that are stacked up, open the cabinet right above it.
Over there.
No, don't do the. Oh, yes. Sorry, I thought you picked. What? No, oh, you did pick an old one. Okay, hold on. Pick a new one. Pick from the center. Pick from the center. Yeah, from the center. There you go. They're the new ones. I'd rather people pick the new ones first rather than the used ones. I'm sorry, you said my name for half a second.
I forgot.
Oh, I thought it was you. Okay, so he sounded like you. Why do they let me do this for free? Anyway, a polynomial is an equation where all exponents are positive whole numbers. Let me get rid of this. That's pretty good. A polynomial is an equation where all exponents are positive whole numbers. No negative numbers, no fractions, no decimals in the exponent. Mind you, specifically in the exponent. An example being y equals 2x plus 1. This is a linear equation. It is also known as a first-degree polynomial because the largest exponent is just a 1. Y equals x squared plus x minus 6. This is what we've called a quadratic. And a quadratic is a second-degree polynomial. Largest exponent is a 2. Now, typically, these equations are written where they have all the variables in order. The order is typically largest exponent to smallest exponent. You could also have y equals 3x cubed minus 4x squared minus 17x plus 6, which we're going to take a look at in a moment. This is a cubic equation. Largest exponent is a 3. So I want to type that one into Desmos. Real quick here. I'm actually going to do it as f of x. F of x equals 3x to the third minus 4x to the second minus 17x plus 6. Look at that. That's fun. That is the polynomial that we have in question. It is a third-degree polynomial. Now, a lot of the things that you are going to be asked to do are very similar to what we did in the previous chapter, or the previous unit, I should say. You may have to solve this problem. You may have to factor this problem. You may have to graph this problem. Unfortunately, the same tactics that we used in the previous chapter may not be helpful. Here's that equation again. I want to do something with this equation. Give me a number, a small number. But don't make it like a 1 or something. 4? Okay. We're going to take 4, the number 4, and we are going to shove it into this equation violently. We are going to evaluate f of 4 with this equation. The 3x cubed minus 4x squared minus 17x plus 6. We're going to stick with this equation for a little bit. Let's just see what happens with it. So if I evaluate this thing at f of 4, logically, I got to take that 4 and I got to plug it in for all of the x's. I got to plug it in for all the x's. Now, you picked the number 4. I didn't do this calculation beforehand, so I am going to have to do this one by hand a little bit here, or by hand. I'm going to have the calculator do it, really. Use parentheses. Parentheses are going to be your best friend. Double check, make sure. Oh, nope, I did not type that in correctly. I didn't put the square in there. There we go. Double checking. Good. 66. Right on the dot. Now, this means a lot. This means a lot right here. The fact that this is 66. I'm going to double check this on Desmos in a moment. The fact that we got 66. F of 4 equals 66. Now, this has meaning. This has consequences. It means that the ordered pair 4, 66 is a point on the graph. It means that that ordered pair, the input of 4, the output of 66, is a point on my graph. Let me go back to the graph. Let me go back to the graph and kind of see what this thing looks like with that. Now, the 4 is way up there, but I can do this. Boom, look at that. On the far left side, in the left column, I did F of 4, and it spit out a 66. Excellent. But that is an ordered pair on the graph. It's somewhere, oh, I passed it. Somewhere over here. Right about there, 4, 66. There it is. Pretty solid. Let's go back here. Can you guess where this thing might cross the x-axis? What value or what number could you put in for it to cross the x-axis? Like, it crosses the x-axis 3 times, right?
Yeah.
Where? What number? What value? Looks like a 3. Yes, where else? Ooh, -2, definitely. There's the third one right there. 1/3. That was a little tougher. The fraction was a little tougher because it's like, where exactly is it? I don't know. But the -2, definitely. Let's do something. Let's plug in that -2. F of -2. You have to be very careful with these negatives. I've said it from the beginning of the year that parentheses will save your life. You need to make sure that you are utilizing parentheses correctly. Now, we already know what the value should be. We'll go back to the graph real quick. If I plug in a -2, what should be the output? Looking at this ordered pair right here. It should be 0. It should be 0. I'm going to confirm that in a moment. But it should definitely be 0 as the output. Let's see. I'm going to go 3 parentheses, -2, -2 cubed, minus 4 parentheses, -2 squared, minus 17 parentheses, -2, plus 6. Now, the logic of this is that the calculator with all of these messed up numbers and messed up exponents and messed up negatives, boom, equates exactly to a 0. It equates exactly to a 0, which is nice. Now, that's helpful because that tells you something. It tells you f of -2 is equal to 0. Thus, the ordered pair -2, 0 is a point on the graph. This is important. This is very important. Now, we got 2 ordered pairs here. I want to do something with that 4 and that 66 in a moment. And I will eventually do something again with that -2 and that 0 as well. I want to show you something. I want to show you something that you've never seen before in your life. I'm pretty confident that you've never seen this before. Here's what I want you to do. Write down this equation again. Write down this equation again. I want to stick with this equation. I'm not going to leave this equation behind just yet because I'm not done with it. Same example. And I want to evaluate f of 4. Now, we already know what f of 4 is. We already know what will happen. What should be the result of f of 4? What should be the output when we plug a 4 into the equation? Should be, and it will be. It will be. But I want to show you something special. It's that. Oh, you can't see it. It's that. What the heck is that? Kind of. It's a bar. It's a bar. It's a synthetic bar. What the heck is a synthetic bar? I'm about to show you something. This bar is going to be the most important tool that you use during this new unit. Trust me when I say it will be. First, I'm going to put those numbers across the top. Where the heck did you get those numbers from? Do you know what they're called, those numbers? They have a special name. Starts with a C, ends with an O efficients. There you go. It worked. They're coefficients. They're the coefficients of the graph in order. In order. Largest to smallest exponent. Not largest to smallest number, largest to smallest exponent. Next, I'm going to put this number right here. That number is the number you plug in. That's the number that you plug in. Now, I promise you that when I'm done showing you this bar and how it works, the end result is going to be a 66. And this bar, as I said, is going to be one of the most important things that you use over the course of the school year. Here's how it's going to work. This bar does a repeated mechanic between adding and multiplication. It goes back and forth between adding and multiplication. Adding is always done vertically, straight up and down. Multiplication is always going to be by the number that you're plugging in right here. It's going to go back and forth, adding, multiplication, etc. It's going to keep going back and forth, and the end result is going to be a 66. Watch what happens. First, I'm going to add. I'm going to add vertically 3 plus, nothing. Well, I guess that 3 just comes straight down. That's anticlimactic. Okay. Now that we've done the adding, let's go to the multiplication. I'm going to multiply 3 times 4. I get 12. Where do I put the 12? I'm going to put it in the next blank spot. 3 times 4 gives you 12. All right, well, I did adding, and then I did multiplication. I got to go back to adding. So I'm going to add vertically. I'm going to add vertically right here, and I get a positive 8. All right, that's right. Somehow this is going to get you a 66. Okay. I'm going to go back to multiplication because you go back and forth and back and forth. I'm going to multiply 8 times 4. I got 32. 32, I'm going to put in this blank spot. All right. Now I'm going to go back to adding. I'm going to add these 2 vertically. If you did that correctly, I believe that you should be getting a 15. 15, right on the dot. Some of you have already figured out it does get you a 66. I know you have already jumped ahead with that, but let's see what happens. I'm going to go back to multiplication. I'm going to multiply together the 15 and the 4. 15 times 4, you can do that in your head. That's 60. And then finally, I add vertically. I add vertically, and it gets me a 66. This is the number you get back. This process that I have just outlined for you is something called synthetic substitution. It is called synthetic substitution, and it is one of the most important things you will learn over the course of this new unit. This method, this process, has far-reaching implications. This process is going to be very important in regards to some of the higher-level polynomials that you will see over the course of this chapter. Let's see what we're going to do with it. Let's do it one more time. I'm going to have you do it with a different number. Scroll that up. I'm going to have you do it. Create a new bar. And literally, this should take you like 15 seconds or less. I'm going to have you plug in a -2. Now remember, that -2 is the number that you plugged in. What are we supposed to get back according to what we did earlier? Well, what happened when we plugged in a -2? What did we get? We got 0 as a result, yes. So we should get 0 again here. Do it, 15 seconds or less. Knock this out. Nothing more than repeated adding and multiplication.
This is 20.
20th?
Oh, I got 20.
20? You have 20?
I got 20.
What's that mean?
Did I answer?
20 what?
Big number, right corner. Thank you so much.
Oh, that was loud. All right, like I said, what? Now, honestly, watch how fast this can go once you get the hang of it. 3, 6, 10, 23, -6, 0. Boom. That is going to be very important, knowing how to do that. This, as I said, is called synthetic substitution. It is called synthetic substitution. F of -2 is equal to 0. I have a definition that I want to give you in the form of a bullet point. Here's a little definition that I want to give you. Not to bring back a lot of PTSD for you, but you all remember geometry? Yeah. I have if-then statements for you. If f of k is equal to 0. Now, k is just some number. It's just some number that maybe we know it, maybe we don't. But if f of k results in a 0, just like the previous example, then k is a, quote, 0 of the function. If f of k is equal to 0, then k, whatever that number is a 0 of the function. What's another name for a 0 of the function? We've called it so many different things. What else have we called zeros of the function? There's like 4 total names that they all meant the same thing. Roots. What else? x-intercepts, yep. Last one was a little trickier, just because it was very generic. Solutions. It was a very generic one, but x-intercept is another key one, because literally we saw the x-intercept. We saw the x-intercept. If f of k is equal to 0, then k is a 0 of the function. So let me show you what you're going to do over the course of this chapter. I may give you a sample problem like this. I may say, hey, here's an example, different problem, f of x equals x cubed minus 6x squared plus 13x minus 10. And I may say, hey, find me an x-intercept, or solve the equation, or something along those lines. Find me the zeros of that function. And you're going to be like, how do I start? Because typically people would be like, okay, oh, by the way, if I'm going to fill out this bar, what numbers do I put here? What number do I start with? Yes, a lot of people miss that, but it is a 1x cubed. Yes, 1, -6, 13, and -10. The biggest question that people have, and I'm going to point my pen at it. What number do I put there? Here's the thing. At this exact moment, we have no idea. At this exact moment, we have absolutely no idea. What number do we put on the outside of this bar? How do I figure that out? Well, I'm not asking you guys to take them out now because I'm going to do it on my calculator, but you guys have graphing calculators on your Chromebooks, right? And if this were a normal year, you would have graphing calculators to use in my classroom. Here's what you're going to do. Kind of. Not exactly guess and check. You would actually do something like this. You would look at the graph. You would look at the graph. You would type it into your y equals key. You all have graphing calculators on your Chromebook, so you can do this. And when you graph it, keep in mind that you are trying to identify an x-intercept. You are trying to identify, okay, if I say, find me the zeros of the function, I'm really saying, find me where it crosses the x-axis. Now, the problem with this is that, oh my gosh, I am not entirely certain where it crosses. So you said guess and check, and I said kind of. Let's try it. Let's just try. That's what I'm saying. That's why I say it's kind of guess and check. Because visually, it's like, I think it's a 2. It could be a 2.5. Let's try it. So hold on. Let's go back to our notes real quick. So we think 2 is an x-intercept. We think it's an x-intercept. Someone get it? We think 2 is an x-intercept. Now, are we guaranteed? No, we're not guaranteed. We are not guaranteed whatsoever. But we think it's an x-intercept. So here's what's going to happen. Over the course of this chapter, I may give you a problem like this one up here. F of x equals that equation. Then I may ask, hey, what are my x-intercepts? What are my zeros? Find them for me. And most people would start, I'm going to cover this up actually. I'm going to cover that up. Most people would start with the synthetic bar, and they would fill it out using those numbers, 1, -6, 13, and -10, based on the 1, the -6, the 13, and the -10. But they have no idea what number to put here. They have no idea what number to put there. No. They asked a good question. He actually asked, like, do we guess and check? And I said, kind of. The reason why it's kind of guess and check is because you all have graphing calculators on your computers. So you can type in this equation into the y equals key. Because if I say, hey, what are the zeros of the function? I'm really saying, what are the x-intercepts? Where does it cross the x-axis? And they told me it kind of looks like 2. Maybe it looks like 2.5 or 2 and some decimal. So that's why I say, he says, is it guess and check? And I said, kind of. Because we think it's 2, but we're not certain. We are not certain. So we think it's 2. So look at the note I put on the side. We think 2 is an x-intercept. We think. So I'm going to put a 2 there. If we are correct, what number should pop up on the bottom right?
0.
A 0, if we're correct. Let's do it. We have to prove it. Let's prove it. So 1 plus nothing is 1. Multiply by 2 is 2. Add vertically is -4. You multiply by 2 again, you get -8. You add vertically, you get 5. You multiply by 2, you get 10. You add vertically, you get 0. This number right here. This proves x equals 2 is a 0 of the function. The fact that you got 0, you can't see it, the fact that you got 0 in the bottom right of that synthetic bar, of that synthetic substitution, it proved that 2 was a 0 of the function. This was the possible 0, but we could not confirm that until we got that 0 in the bottom right. This synthetic bar is going to be so important for you. So important moving forward. Now, here's the thing. If we didn't get 0 here, one of 2 things would have happened. If we did not get a 0 here, then one of 2 things has happened. Number 1, you made a mistake. Number 2, you got the wrong number. And then we may have to go back to guess and checking. So it really depends. It really depends. Always double check first to make sure that you didn't make a mistake. You always have to double check first. I have another bullet point definition for you. Another bullet point definition, which is going to take this thing even farther. Bullet point. Another if-then statement. It starts out the same. If f of k is equal to 0, just like before we had f of 2 equal to 0. If f of k equals 0, then x minus k is a factor of f of x. We, in the past 2 months, have been solving quadratics and factoring quadratics. We have talked about the idea of finding the zeros of the function, of finding the x-intercepts of the function, but also the idea of properly breaking these things apart and factoring them. The synthetic bar that I've introduced to you is going to be a way we can factor these problems. It's going to be amazing. Let me show you what I mean. First of all, let's write down this example, and I want to talk a bit more about this. F of x equals x squared plus 7x plus 12. All right, cool. Yay. Let me go up to the board real quick. We've been seeing this for months. This is a quadratic. We can solve this. We can factor this. Hey, give me 2 numbers that multiply to 12 and add up to 7. Yeah, that was easy. That's how we can factor this thing. Using whatever Tucker method of factoring that you got, here is our original equation. We can factor it into x plus 3, plus 4. You said 4. Because they have to multiply to a positive 12, add up to a positive 7, those numbers work. Those are my factors. What about my zeros or solutions? What would be the solutions of those two binomials? X plus 3 is a factor, which means what's a solution? Remember, you set them equal to 0 when you solve. Yeah. You'd have x equals negative 3 as the 0 of the function. Similarly, you'd have x equals negative 4 as the 0 of the function. Let me show you on Desmos. Let me show you on Desmos. Flip to Desmos. There we go. Get rid of that. Go up here. Let's do it as x squared plus 7x plus 12. Zooming in, zooming in, zooming in, zooming in, zooming in. There's the quadratic. And there are my two zeros of the function. Negative 4 comma 0 and negative 3 comma 0. Now this is important. Let me go back to that definition that I just had before. Let me go back to that definition that we just did on the bullet point. Come on, little microphone. Chapow. Here's the definition. If you have a 0 of the function, if f of k is equal to 0, then, where's my marker? X minus k. Where did I put it? I said the red marker, didn't I? Unless I threw it across the room in anger and a fit of rage. There it is. If f of negative 3 is equal to 0, as this one would, because it's a 0 of the function, then x minus negative 3 would be a factor. What is x minus negative 3 if you had to simplify that? What happens when you do x minus negative 3? You did this back in middle school. Subtracting a negative? What happens when you subtract a negative? No. When you subtract a negative? X minus negative 3? What do you guys do? Like keep, change, change? I don't know how you did it back in the day. No, that's for dividing fractions. What happens with x minus negative 3? You just what? No, you don't just stare at things. When you subtract the negative, look what I just pointed to. Yes! Subtracting a negative means you add a positive because the negatives cancel each other out. Just a little thing right there. It depends on whether you're doing addition or multiplication. If you do a negative plus a negative, you get a bigger negative. If you do a negative times a negative, you get a positive. Oh, there. Like negative 3 plus negative 4 is negative 7. Yeah. Negative plus a negative is a bigger negative. Anyway, let's go to this. Check this out. First and foremost, now this is going to shed some light on why this is important. Something big is about to happen. Something amazing is about to happen. I'm going to put that negative 3 on the outside because negative 3 is a 0. We know it's a 0. We're going to prove that it is a 0. The 1 comes down, you multiply, you add, you multiply, you add. That 0 proves negative 3 is a 0 and x plus 3 is a factor. I'm going to leave this up here for a few minutes because I just want to relish in how amazing this moment was. If you don't recognize how amazing this moment was, I'm going to explain to you why it was so amazing. This moment, this math that is written on the board right now is more important than you can ever imagine. I don't think you've recognized it. First, let's just kind of walk through it. First, I set up the synthetic bar. I plugged in the -3 because -3 was a 0. We saw it on the graph. We got the 0 here. And we got -3 as a 0 and x plus 3 as a factor, which we already knew beforehand. What you have just done is more than just synthetic substitution. You have done something called synthetic division. You have actually, believe it or not, without knowing it, have divided polynomials. Question, what's 28 divided by 7? 4, right? 28 has a 7 in it, right? 28, one of the factors of 28, I'm sorry, is a 7, right? If I take 28 and I divide it by 7, what happens to those 7s? Do you know what happens to the 7s if I take 28 and divide it by 7? They go away. The 7 and the 28 cancels with the 7 on the bottom, and you're left with 4. Here's the thing. If you take 4 and then multiply it by 7, what do you get? 4 times 7. 28. You can go backwards. Look at this. What happens when I multiply these two factors together? If I multiply these two factors together, what am I supposed to get? Just like 4 times 7, I get 28. If I multiply these two factors together, I'm actually supposed to get this original polynomial. You, believe it or not, have just done synthetic division. And you're still at this point like, how, why, where, when? Watch. What you've just done is you've taken this original polynomial and you have divided it by this factor, x plus 3. And you're like, okay, I want to point something out to you. Look at this. You see this x plus 4? That's not a coincidence. That is not a coincidence. Again, believe it or not, yeah, I'm going to show you how it works in a few moments, but you have actually done what is known as synthetic division. Let me show you with a slightly different example how this thing actually plays out. This thing's going to mess with your heads. Actually, no, let me do the same example, but let me kind of do it in more detail. If I were to say, take this quadratic and divide it by x plus 3. If I said, take this quadratic and divide it by x plus 3, just like before when I said, hey, take 28 and divide it by 7. The 7 would cancel out with something, and you'd be left with a result of the division. The result of this division is x plus 4. And if you multiplied these two binomials back together, you'd end up with the original quadratic, but that's not here. Or that's not what I'm doing. This is the same as the following. This division that I have at the top of the page is exactly the same as what I'm about to show you. And I would have you write it down again for emphasis. Question. When you divide something, if you have something left over, what do you call it? Not in division. No. If you divide something and you have something left over, what do you call it? This goes back to elementary school. For example, 28 divided by not 7, 28 divided by 6, you would get 4 with something left over. What's that called? Oh, come on, elementary school math students. You usually,
Pull out every single word that I know.
it usually started with an R. It's your remainder. It's your remainder. It's what you had left over. See, the thing is, this 0 actually indicates what your remainder is. These two things divide perfectly, so you have a remainder of 0. Just like when you did 28 divided by 4, you would get 7, remainder 0. This number is your constant, and this number is your x term. The result of division is 1x plus 4. The result of division is 1x plus 4. This division is going to help you so much because of its far-reaching implications. It is going to basically permeate everything that we do. Not everything, probably like 90% of what we do in this chapter. This synthetic bar, as I have emphasized, is going to be very important. For example, let me do a slightly different example here. I may give you the problem saying, hey, divide the following. I may say, hey, take x cubed plus 2x squared minus 5x minus 6 and divide it by x minus 2. Say, hey, I need you to divide those. I need to know what the result is. And you're sitting there like, okay, I guess I'm going to set something up. Well, I'm dividing polynomials. I'm going to set up a synthetic bar. Move this up a little. I'm going to set up a synthetic bar. And the numbers I'm going to put on the outside, I'm sorry, the inside are going to be this. Question. Because this plays into everything that we've been doing today. What number do I put on the outside? Not exactly. You can't divide it until you run through the synthetic. You can't just divide like the 6 and the 2. You can't do that. Here's the thing. I'm going to give you those two bullet. Remember those two? Oh. Well, that's what I'm trying to do. I can't. No, I can't. I understand what you're trying to say by simplifying. You can't do it. Because well, for example, x plus 6 divided by 2. I can't just say like, okay, 6 divided by 2 is 3. I can't do that because you're dividing both those terms. Yeah. In this case, you're actually dividing every term here by x minus 2. Nope. That would be an illegal math move. That would be a sick bird, an illegal. Yeah, it would be, but why? I gave you 2 bullet points earlier today, right? I said if f of k equals 0, then k is a 0 of the function. I also said if f of k is equal to 0, then x minus k is a factor. Now this is where this is why it's going to be a positive 2 that I put on the outside. X minus 2 is the possible factor. Do I know it'll work? No, I don't know it'll work. I don't know yet. But you're not going to put factors on the outside of this bar. You're not going to put possible factors. You're going to put possible zeros. You have to put possible zeros on the outside. And in this case, x minus 2 would produce a 0 of positive 2. Let me write some notes right here. Hold on. This is a 2. This is the possible 0 of x minus 2. It's a possible 0. I don't know if it'll work. The only way I am going to know that it works is if I get a 0 in the bottom right corner. That's the only way I'm going to know. So let's run through it. 1 plus nothing is 1. Multiply by 2. 2 plus 2 is 4. Multiply by 2. Negative 5 plus 8 is 3. Multiply by 2. Add them up, I get 0. It worked. It worked. This is my remainder, which is 0, which is great. You're not always going to get a remainder of 0, but here we did. This is my constant. This is my x term. Question, what the heck is this? If 3 is my constant and 4 is my x term, then what is 1? Think about it. Constant, x, what comes next? It's a good thought. X squared. It's your x squared term. Meaning the result, the answer, is 1x squared plus 4x plus 3. That is the result of the division. Now, I want to show you one more thing, but it doesn't require you writing anything down. So I'm going to set something up on my graphing calculator right now that I want you to see visually, but I'm telling you that I'm done writing stuff down for the day. Just giving people a chance to kind of catch up on writing this. Now, what I've just done in my graphing calculator is I have put in this equation, x cubed plus 2x squared minus 5x minus 6. I put that into my graphing calculator. Let me zoom in here. And I'm going to graph it. Watch the graph. Look at the graph. That wonderful graph and all of its wonderful stuff. There is x equals 2. There's x equals negative 1. There is x equals negative 3. Watch what I'm about to do. Watch what I'm about to do. This is going to be insane. Watch this, watch this, watch this, watch this, watch this. Now, this is the problem. This is the problem that we were just dealing with. This is the problem where I divided by x minus 2. I'm dividing out the x minus 2. I'm dividing out a 0 of positive 2. Watch what's going to happen. Watch this, watch this, watch this, watch this. What do you notice? But not the 2. Because remember, I divided out x minus 2. I divided it out. And when we divide it out, it goes away. Like 28 divided by 7, the 7 goes away. But if you notice, look, it has the same zeros. It's just no longer a cubic. I divided it. Hey, what was that quadratic that we got? It was like x squared plus 4x plus 3. The result, that's what that quadratic is. Watch this. I'm going to divide it one more time. Hey, pick negative 1 or negative 3. Pick one. Negative 1. Watch this. Now keep in mind, even though you pick -1, it's x plus 1 as the factor. Because we went from a cubic down to a quadratic, down to a linear. It's the only 0 remaining. Ladies and gentlemen, we're going to pick up with more of this on Tuesday. Yes, I see you Tuesday. It's going to be great. I'm going to end the live stream from there, and we'll see you then.